Hey there, tech enthusiasts. Have you ever been blown away by the stunning visuals in modern video games? Games today look so real, it's like stepping into another world. Think about the incredible detail in games like Cyberpunk 2077 or Red Dead Redemption 2. We're talking vast, sprawling landscapes, lifelike characters with realistic skin and hair, and special effects that'll make your jaw drop. But how do computers actually create these amazing 3D worlds? How did they take a bunch of code and turn it into something that looks so real? Well, buckle up because we're about to dive into the fascinating world of 3D graphics. We're going to break down the secrets behind the technology that powers these incredible visuals, from the basics of the rendering pipeline to advanced techniques like ray tracing. Get ready to learn how your computer transforms simple shapes into the breathtaking digital landscapes we all know and love. This is more than just pretty pictures, though. Understanding how 3D graphics work gives you a whole new appreciation for the power of your gaming rig. It's like peeking behind the curtain to see the magic happen right before your eyes. So let's get started and explore the incredible world of 3D graphics. Now, before we get into the nitty-gritty, let's talk about the rendering pipeline. Think of this as the step-by-step process your computer uses to create those stunning 3D images. It's like an assembly line, but instead of cars, we're building virtual worlds. First, we start with a bunch of 3D models made up of polygons. These are basically just shapes like triangles connected together to form objects, kind of like digital Legos. These models are then sent through the rendering pipeline, which consists of several key stages: Vertex Shading, Rasterization, and Fragment Shading. Each stage plays a crucial role in transforming those basic shapes into the final image you see on your screen. Vertex Shading manipulates the position and orientation of each vertex in a 3D model. This is where we apply transformations like moving, rotating, or scaling objects in the scene. Rasterization takes those transformed vertices and converts them into pixels on your screen, figuring out which pixels are covered by each polygon. Finally, Fragment Shading determines the color and lighting of each individual pixel, making your 3D world come to life. It's a complex process, but understanding the basics of the rendering pipeline will give you a much better grasp of how 3D graphics actually work. And trust me, once you start to see the magic behind the curtain, you'll never look at video games the same way again. All right, let's dive into the first stage of the rendering pipeline, Vertex Shading. This is where things start to get really interesting. Remember those 3D models made of polygons we talked about? Well, each corner of those polygons is called a vertex. Vertex shading is all about manipulating those vertices to position and orient our 3D models in the virtual world. We do this using something called matrix math, which sounds complicated, but is actually pretty cool once you wrap your head around it. Basically, matrices are just arrays of numbers that we use to perform transformations on our vertices. We can use them to move objects around, rotate them, scale them up or down, and even combine these transformations together. This is where your GPU, or graphics processing unit, really shines. GPUs are specifically designed to handle the massive number of calculations required for 3D graphics. They're like math whizzes that excel at matrix multiplication, making them perfect for the job of vertex shading. So during vertex shading, the GPU takes each vertex of our 3D models, applies the appropriate matrix transformations, and spits out the transformed vertex data. This data is then passed on to the next stage of the rendering pipeline, where things get even more exciting. Now that we've transformed our 3D models using vertex shading, it's time to turn those vertices into something we can actually see on our screens. Pixels. This is where rasterization comes in. Imagine you're coloring in a coloring book. You have your outline, which is like our transformed polygons, and you need to fill it in with color. Rasterization is like the process of figuring out which tiny squares on the page, our pixels, need to be colored to represent the shape. The rasterizer's job is to determine which pixels are covered by each polygon in our scene. It does this by looking at the edges of the polygons and figuring out which pixels fall within those boundaries. This is also where we deal with visibility, making sure that objects closer to the camera obscure objects that are farther away. To handle this, we use a clever technique called Z-buffering. Think of it like a depth map of our scene where each pixel is assigned a depth value. When rendering a polygon, we compare its depth value to the depth value stored in the Z buffer for that particular pixel. If the polygon is closer, its depth value is written to the Z buffer, ensuring that only the closest objects are visible. Once the rasterizer has determined which pixels are covered by which polygons, it passes this information onto the final stage of the rendering pipeline, fragment shading. This is where we add color, lighting, and all the other good stuff that makes our 3D worlds come to life. We've reached the final stage of the rendering pipeline, fragment shading. This is where we transform flat polygons into a vibrant, believable world. Rasterization told us which pixels are covered by each polygon. Fragment shading decides what color each pixel should be. We factor in lighting, shadows, textures, and special effects. Fragment shaders are tiny programs that run for each pixel. They calculate the final color of each pixel. Fragment shading allows developers to create stunningly realistic 3D graphics. Section 6. Smoothing out the rough edges, normals, and barycentric coordinates. We've come a long way in our journey through the rendering pipeline. One trick is smooth shading, which helps us achieve smoother, more natural-looking surfaces. 3D models are made up of polygons which are flat surfaces. Shading each polygon with a single color gives a faceted look. Smooth shading interpolates colors, creating a rounded appearance. We use vertex normals, vectors perpendicular to surfaces. Assigning normals to vertices and interpolating them approximates surface curvature. This is done using barycentric coordinates representing a point inside a triangle. Smooth shading enhances the realism of our 3D graphics. Section 7. Ray tracing and DLSS, pushing the boundaries of realism. We've covered the basics of the rendering pipeline, but the world of 3D graphics is constantly evolving. Today we have even more advanced techniques at our disposal, like ray tracing and DLSS, that are pushing the boundaries of realism even further. Ray tracing is a rendering technique that simulates the physical behavior of light. Instead of approximating lighting and reflections, ray tracing actually traces the path of individual rays of light as they bounce around the scene. This allows for incredibly realistic lighting, reflections, and shadows, making our 3D worlds look more believable than ever before. However, ray tracing is incredibly computationally expensive. That's where DLSS, or Deep Learning Supersampling, comes in. DLSS uses the power of artificial intelligence to upscale low-resolution images to higher resolutions, while maintaining image quality and even enhancing it in some cases. This allows us to enjoy the benefits of ray tracing without tanking our frame rates. These are just a few examples of the cutting-edge technologies that are shaping the future of 3D graphics. As hardware and software continue to advance, we can expect even more realistic and immersive gaming experiences in the years to come. Section 8. The future of graphics, a world of possibilities awaits. The world of 3D graphics is a constantly evolving landscape. What seems like cutting-edge technology today might be commonplace tomorrow. As we continue to push the boundaries of what's possible, we can expect even more realistic and immersive gaming experiences in the future. Imagine worlds so detailed and lifelike that you can't tell the difference between the game and reality. Imagine games with truly intelligent characters that react and respond to your every move. The possibilities are endless. With advancements in virtual reality and augmented reality, we're on the cusp of blurring the lines between the digital world and the real world. The future of 3D graphics is bright, and we're only just scratching the surface of what's possible. Section 9. Join the revolution. So there you have it, a crash course in the fascinating world of 3D graphics. We've covered a lot of ground, from the basics of the rendering pipeline to advanced techniques like ray tracing and DLSS. But this is just the beginning. Now that you have a better understanding of how these incredible visuals are created, it's time to experience them for yourself. Fire up your favorite game, crank up the graphics settings, and prepare to be amazed by the power of modern technology. And if you're feeling really adventurous, why not try your hand at creating your own 3D graphics? There are tons of resources available online to help you get started, and who knows, maybe you'll be the one pushing the boundaries of what's possible in the future.